हेलो देशिका।
Yes, sir.
දේශිකා සුබලුත් අවුරුද්දක් වේවා.
Nineteen වේවා සර්.
දේශිකා මේ ඔයගලන්ගේ ගෲප් එකට මැසේජ් එකක් දාන්න. මම
හා
ලෙක්චර් එක පටන් ගන්න කියලා. තාම නෑනේ කට්ටිය ඔයා විතරයිනේ ඉන්නේ ඒකයි මම බැලුවේ. හරි පොඩ්ඩක්
හා
බලන්නකෝ.
සර්. ඕකේ සර්.
ඕකේ. Okay. I think it's time to start the lecture. Deshika, you are there, right? උදේශිකා ඉන්නව නේද?
Yes, sir.
Okay, okay. Now, I thought to give you a kind of reminding session which we discussed last time. Last time we discussed about the shear strength of soil and its basic principles were also discussed during the lecture. So I hope you all remember, like we say when we talk about the construction materials, each construction material has been used in construction industry because of its specific characteristic. So, steel, it is for tensile strength. Concrete, it is for compressive strength. Likewise, when we check about the soil as a construction material, we see soil undergoes compression well, but before it reaches to the compression criteria, it fails. So, that failure we say as the shear. So most of the failures coming from due to the soil, most of the failures we observed in soil are due to the shear, right? So the shear strength and associated theories are really much important for you to study as civil engineers. So now we say shear strength is depend on two important parameters, that is cohesion and internal friction. And then we discuss about what is cohesion, what is internal friction. Hope you all remember these things. We say cohesion is the particle bonding between each other. Frictional resistance is actually when particles are moving from each other, on each other, there's a resistant force, the friction force, that depends on the interlocking arrangement between the soil grains. So we discussed about that thing as well. So we said cohesion is a kind of material property, friction is a kind of stress dependent component, right? So accordingly, we discuss about several important basic theories. We say this is Mohr-Coulomb failure criteria, and we derived some equations from there on, right? Hope you all remember these things. So we completed up to this point, and then from there onwards, we are going to discuss now from this slide onwards, right? So as I said here, it's very important topic in terms for the civil engineers, and because of that thing, many theories and many principles have been developed in order to determine the shear strength of a given soil. Because as I said short while ago, most of the failures uh, available in soil are depend on the shear failures, right? So most of the failures are shear failures, right? So soil, in terms of soil, these shear failures are really important. So because of that, in order to determine the shear strength, several tests, several theories have been developed, right? So now we can categorize the test associated with shear into two. First category is laboratory test. Second category is field test, right? So, laboratory test, we have direct shear test, unconfined compression test, triaxial test. Likewise, there are many tests available. Also, field in situ tests are available. So, vein shear test, Towens test, pocket penetrometer test, likewise, fold cone test, pressure meter test. Likewise, there are many testing available in order to determine the shear strength parameters, right? So, this laboratory test, in this module, we are discussing about this laboratory test. And the laboratory test we are focusing on direct shear test, unconfined compression test, and triaxial test only, right? So we will go one by one. We will discuss one by one. You may have studied these things in your previous studies, but it's better if we discuss these things with the understanding of shear principles, right? So moving on to direct shear test. Okay. Now, as you know, this is a kind of ground condition at rest. Means there's no external force in this situation. You can see it is a bare ground. So when we consider a soil point underneath the soil surface at Z depth, so we can see the horizontal stresses are applied. It is equal and opposite in each direction. So you can see sigma h and sigma h, and the direction of the arrows you can see. So and the other thing is you can see here sigma v is available. Those are the vertical stresses, right? So these all are at rest. So no imbalance forces are available. But when you construct some kind of structure over the ground, what will happen? A vertical stress will be increased, right? So there's a deviatoric stress, or we say increased stress on the vertical stress due to this structure, right? That is well understood. Okay. So, sorry. So we are now discussing two important tests. First thing is direct shear test. The other thing is triaxial test. So we are simulating these site conditions in lab situations, right? So what we are doing is for direct shear test, we made the soil sample to fail on a predetermined shear surface. So what we are doing is once we apply the vertical stress, we apply shear force. So when we increase this shear force, when we increase this horizontal force, what will happen? There's an instance that the soil will be failed on this predetermined surface, right? So that's what we do in direct shear test. I am repeating, in direct shear test, what we are doing is we are now we are now asking the soil sample to fail under a predetermined surface. This surface is predetermined. Okay. This red line is predetermined. We know, okay, the soil will fail under this surface. Okay. So, and then we apply certain vertical stress, and then we apply the horizontal forces, right? So, once you apply the horizontal force, the soil will not be failed, but to increase the horizontal force, there is a chance for failure, right? So that failure will be happen on that predetermined surface marked in red color, right? So the bottom figure, this one, is for the direct shear test, right? So in terms of triaxial test, it is somewhat different. There, what we do is we do not do kind of predetermined surface. We made available the horizontal forces, and then we made available the vertical forces as well, right? So once we increase the vertical stresses, the soil will freely uh, failed under a unpredetermined surface, right? So this red color line, you can say it is a inclined surface. So in the inclined surface, the soil will be failed. So that's what the difference between the triaxial test and direct shear test, right? So when we talk about these things, it is clearly evident that the triaxial test is it is somewhat closer to the realistic situations. But when we talk about the direct shear test, what happen is we are allowing the soil sample to fail under a predetermined surface, right? So this is a predetermined surface. So because of that thing, the soil may have kind of weaker surfaces which we don't know, right? Understood? Hmm? ට්‍රයක්සියල් එකේදී අපි මොකද කරන්නේ? ට්‍රයක්සියල් එකේදී අපි සොයිල් එකේ horizontal force stresses දෙනවා. vertical stresses දීලා vertical stress වැඩි කරන් යනකොට එයා කැමති weak soil pain එක එයාට නිදහස තියෙනවා. එයා fail වෙන්න. නමුත් direct shear test එකේදී මොකද වෙන්නේ? මේකේ සමහරක් විට weak surfaces ඇති. නමුත් අපි එයාට කලින් දීලා තියෙනවා ඔයා මෙන්න මේක හරහා fail වෙන්න. එතකොට practical මට්ටමින් ගත්තහම මේක ටිකක් ප්‍රැක්ටිකල් වැඩි ට්‍රයක්සියල් ටෙස්ට් එක. මොකද අපි අර ෆ්‍රීලි ෆේල් වෙන්න නිදහස දීලා තියෙනවා. දැන් ඔයා හිතන්න මේකේ ඩිරෙක්ට් ෂියර් ටෙස්ට් එකේ මෙන්න මේක හරහා තමයි ෆේල් වෙන්නේ. නමුත් ඇත්තටම මේක එච්චර මේ වීක් සර්ෆස් එකක් නෙවෙයි. එතකොට මේකේ මොබිලයිසේෂන් ෂියර් එක වීක් සර්ෆස් එකකට සාපේක්ෂව වැඩි. තේරුණා නේද? මේක වීක් සර්ෆස් එකක් නෙවෙයි. ඒක නිසා මොකද වෙන්නේ? දැන් ඔයා හිතන්නකෝ මේකේ මොබිලයිසේෂන් ෂියර් ෆේලියර් එකේදී මොබිලයිසේෂන් ෂියර් ෆෝස් එක 150ක් කියලා. නමුත් ඇත්තටම මේකේ තියෙන්න පුළුවන් තවත් සර්ෆස් එකක්. ඒ සර්ෆස් එකේදී හිතන්නකෝ ඉන්ක්ලයින් වීක සර්ෆස් එකක් තියෙනවා. අර මේ සර්ෆස් එකේදී මේක 150 වුණාට ෂියර් ෆෝස් එක මේ සර්ෆස් එකේදී මේක 100 වෙන්න පුළුවන්. නමුත් අපිට ඒක ඔබ්සර්ව් කරන්න chance එකක් නැහැ ඩිරෙක්ට් ෂියර් ටෙස්ට් එකේදී. හේතුව අපි මේ සොයිල් සාම්පල් එකට මේ horizontal surface එක හරහා ෆේල් වෙන්නේ කියලා කියලා තියෙන නිසා. Okay. Hope you understood. Now, what I discussed was there are two tests, triaxial test and direct shear test. What we do is the site condition we will simulate to the lab conditions. There, we apply horizontal forces in triaxial test conditions, and we apply vertical stress. Once we increase this vertical stress, the soil sample will fail on a weaker surface, right? So that you will get the uh, shear shear strength of the given soil. But when it comes to the direct shear test, what happen? Uh, what we do is we apply the vertical stress and we increase the horizontal stress, right? So we apply a gradually increased vertical stress. So what will happen is we give a surface to fail. So that's what I say. There may be some surfaces which is weaker than this surface. So as a result, what will happen is the soil sample will not have a chance to fail under its weaker surface. So the correct shear strength of the given soil may not be uh, expressed in direct shear test. Okay. So this is the direct shear test apparatus. Hope you all know this one. For your understanding, I will say what happened here. You can see there are two boxes, right? I may say shear boxes, direct shear boxes, right? So these two boxes will be filled with the soil, the sand, right? So there will be certain vertical force will be applied, and once we gradually increase the vertical force, you see there are two boxes, no, upper box and the lower box. Now this lower box is connected to this arm. Once we apply the horizontal force, this lower box will try to move, try to translate from the upper plate. Upper plate will be stationary, it will be not moving. But since we apply the horizontal force to the lower plate, it will be trying to um move through the upper plate. So you can see the vertical stress is applied. Horizontal force will be gradually increased. So there is a chance, there is an instance. So at that instance, what will happen? This soil sample will be moved from this from each soil's layers, right? Okay, let me show you. So these are the two boxes, right? So upper box and the lower box. So what will happen? There are two porous plates, right? So corrugated porous plates will be there, right? So now we will first, let's say this is the um, lower mold, this is the upper mold, right? So we first fix the porous plate, right? And then uh, after that, we will combine two boxes, right? So it's like this. Then we um, uh, fill the shear boxes with a given soil, right? Normally, we are using dry sand or kind of normally consolidated clay in direct shear test. So after that, what we will do is we keep the upper porous plate on the top of the soil sample, right? Why we provide these porous plates are the reason. Now you know, okay. Now this is the upper plate, this is the lower plate. Lower plate is connected to this horizontal force. So once you apply the horizontal force, the soil sample will try to move, right? So the bottom plate will try to move, right? So somebody can say not only this soil sample will be moved, but also there will be certain shear forces applied on this soil to uh, bottom of this plate, and then soil to top of this plate. right? You understand, right? It is like this. So these are the shear box, right? Okay. So this is the bottom plate and top plate. So bottom plate will be pushed away. So it will try to move. Firstly, it will not move, but when you increase the force, what will happen? It will move. It will try to move. So somebody can say shear forces have been mobilized in this direction. So shear forces have been mobilized in this plane, right? Simultaneously, the shear forces can be available in this surface as well, right? In this surface as well, there can be some shear forces. So, if so, our shear force measurement uh, cannot be accurate, right? To say now, let's say you have made available the horizontal force, and it is now moving. So you what you do is now this is your shear force. So you may say, okay, shear strength of this soil will be F. But somebody can say F is not only the shear mobilized into soil surfaces, but also the shear forces mobilized in uh, this porous stone to soil sample and this lower box to soil sample. This surface also some shear forces can be available. Somebody can say. To avoid that one, we are introducing these two porous stones. As you see, these porous plates are made available as um, corrugated surfaces, right? So, as you know, the corrugated surfaces shear forces. It's porous plate. Understood? Now, මම මෙතනදි පල්ලෙහා තියෙන තට්ටුවටනේ පල්ලෙහා තියෙන shear box එක. එතකොට shear box එක මෙයා මෙහෙට තල්ලු කර කියන්නේ අපිට කියන්න පුළුවන් මේ ඇප්ලයි කරපු ෆෝස් එක තමයි මේ සොයිල තියෙන shear strength එක. right? මොකද shear එක මොබිලයිස් වෙලා තියෙන්නේ soil to soil අතර ඉන්ටර්ෆේස් එකේ තමයි. නමුත් සමහර එකෙන්ට කියන්න පුළුවන් නෑ නෑ soil to soil විතරක් නෙවෙයි මේ තියෙන soil sample එක මම මේ කතා කරන්නේ මෙන්න මේ තියෙන surface එක ගැන. හොඳේ? දැන් එතකොට තවත් එක්කෙනෙක්ට කියන්න පුළුවන් නෑ upper plate එකයි soil sample එක අතරයි lower plate එකයි soil sample එක අතරයි shear force mobilize වෙනවා. ඒක නිසා ඔයාට මේ shear force එක මෙතනින් ඔයා observe කරන shear force එක මෙතනින් mobilize වෙච්ච shear force එක කියලා ගන්න බෑ කියලා ඔයාට කියන්න පුළුවන්. ඒක නවත්තන්න තමයි අපි මොකද කරන්නේ මේ porous plates දෙක දාන්න. porous stones දෙක දාන්න. ඔයගලන්ට පේනවා ඇති porous stones දෙක ගත්තාම මේ porous stone දෙක corrugated. මේක නිකන් රැලිටි විදිහට තමයි තියෙන්නේ. රැලි විදිහට තියෙන්නේ. ඔයගොල්ලෝ දන්නවා රැලි විදිහට තියෙනවා නම් ඒක හරහා movement එකක් වෙන්නේ නැහැ. shear force එක ගොඩාක් වැඩි. right? ඒ හරහා movement එකක් වෙන්නේ නැති හින්දා ඔයාට මේ ටික neglect කරලා දාන්න පුළුවන්. right? මේ ටික neglect කරලා දාලා ඒ වෙනුවට මේ mobilization shear එක තමයි මෙතනින් read වෙන්නේ කියලා කියන්න පුළුවන්. okay? right? Hope you understand. If anything to be clarified, please let me know. Right? So as I said, the first step would be to preparation of the apparatus. So there we have two porous plates, and then this is the loading plate, and this is the bottom plate, this is the upper plate, and then we have the soil sample. So what we do is we first assemble the lower plate and lower box and upper box, and then fill sand or soil given to you. After that, we have to make it level and then apply the top porous stone and then load in lid, load in pressure plate. Okay, so that lid we have to cover. And then what we do is we normally apply a kind of vertical load, right? And then vertical load will be applied. After that, we will the low box will be subjected to the horizontal displacement. at a constant rate, right? So that force will be um measured through this proven ring. Okay. So the vertical stress is applied and the horizontal stress will be applied and it will be increased until this soil plates are moving apart, right? So the mobilized shear will be measured in this shear box. Okay, right. So that's how this direct shear test will be there. So as you can see, this is the complete apparatus you can see over here. So this is how this vertical stress have been applied on the soil sample, right? So the calculations will be like this. So for shear, uh, if you are applying for shear, even though it is direct shear test, even though it is private shear test, the formula you have to use is tau is equal to C plus sigma tan phi. Tau is equal to C plus sigma tan phi. So that would be the equation. So now how to evaluate the normal stress? Very easy. As you can see, so this is the normal stress, normal force, and then you have the applied area, right? So force divided by area will be given by the normal stress. Normal force divided by cross-sectional area of sample. Shear, on the other hand, you can see the applied horizontal force will be like here, and then shear will be mobilized along the surface, right? It will be mobilized along the surface. So this cross-sectional area along the surface will be the shear area, right? So that's why I mentioned shear resistance developed at the sliding surface divided by cross-sectional area of the sun, right? So you can see the normal stress. When it comes to the normal stress, anyway, the upper plate will be not moving. It will be at the stationary position. And once you apply this vertical stress, so the area will not be changed, right? But when it comes to the shear, what happened? This entire soil body will be moving to this direction. So the touching area, if you are going to evaluate the shear stress, shear force will be F divided by, there should be a area, no? That area means the touching area. But when the sample is moving to the right hand direction, what will happen? This touching area will be reduced time to time. It will be reduced in time to time, right? So those impacts you should mention. Now that's what I mentioned. The cross-sectional area of the sample, this one, will be AC is equal to A naught minus B into H. What is A naught? A naught is the original area, original cross-section area. AC is the corrected area. B, it will not be changed. Then we have delta H sample deformation, right? So hope you understand, right? Now it's like this. Let's say this is your initial position. So this is upper plate and lower plate. So once you apply this horizontal force, this will be subjected to certain change. So let me enlarge the view. So this is the same soil sample, but because of the action of this horizontal force, bottom plate has been shifted to right hand side. You can see, right? So now, so this is the section. So the other section, other direction also, we will have something like this, right? So that width will be B. Think in 3D view. So this one will be B, width of this sample. When you calculate the length of the sample, you can see here the change in the area, change in the length will be delta H. So that delta H you have decrease, right? So that's what V into delta H is, right? Okay, understood, right? Now we discuss about the direct shear test analysis of results, right? So if you are going to mark the shear stress in y direction and shear displacement in x direction. So in that situation, what would be the graph, right? So shear displacement is the displacement we observe, the movement we observe. And shear stress is the mobilized shear stress along the failure surface. So you can see once you increase the shear stress, once you increase the shear displacement, the shear stress will be gradually increased, right? Once you increase the shear displacement, shear stress will be gradually increased up to a certain point, right? After that, it will going down and it will be becoming a constant value, right? So the shear stress will be first it will be gradually increased and then it will reach to its maximum value, and after that it will be going down and it will be keep constant at the end, right? So let's say um, when you discuss about the normal stresses, if we have less normal stress, so in that situation, the mobilize, the higher, the maximum point of tau will be somewhere here, tau F1. But if you increase the normal stress compared to sigma 1, now sigma 2 is higher. So in that situation, tau F2, tau F2 will be somewhere here. It is more than this one. When you increase more normal stress, what will happen? Shear force, shear stress will be getting increased. So very simple, no? Let's say you have applied 50 kilogram here. So you may create certain shear displacement. Now let's say you apply 100 kilogram as normal force. Then your mobilized shear force will be little higher than the previous situation, 50 kilogram situation. Understood? Now, if you apply more and more load, the effort you need to move this soil body will be higher, right? That is very clear. That's what mentioned in this graph. So in this graph, it is mentioned if the normal stress is lower, the mobilized shear stress will also be lower. But when you increase the normal stress, what will happen? The mobilized shear will be getting increased. Okay. So there's another graph. So in y-axis we have shear stress at failure, and x-axis we have normal stress sigma. So this is somewhat what we call this as more Coulomb failure envelope. So if you graph this uh, shear failure stages at different normal stresses, like for sigma 1 we have tau f1, for sigma 1 we have tau f1, for sigma 2 we have tau f2, for sigma 3 we have tau f3. So you can see it is in line. And one more thing, since the direct shear test is mostly done for dry sand and naturally consolidated soil, so because of that thing, normally cohesion becomes zero or closer to zero. Dry sand means no cohesion, no particle bonding, right? Only if the clay is presented, in that situation there is C value, cohesion value. But in this situation, we are using dry sand, no? So as you know, dry sand, we do not expect cohesion in between the particles, right? So likewise, if you made the graph here, y-axis shear stress, x-axis we have normal stress. So for sigma 1, we have tau 1. For sigma 2, we have tau 2. So we plot each other. So we can make a line so that this line, the intercept should go through the origin, right? So it should go through 0, 0 Cartesian coordinate because no cohesion will be available for this particular soil. Okay, right. Now let me show you stress strain relationships for direct uh, direct shear test. Now we have loose sand and dense sand, right? Dense sand means what? You have already compacted, right? Dense sand. Loose sand means you have not compacted yet. That's the physical meaning. Similar concept will be available to OC clay and NC clay. NC clay means normally consolidated clay. OC means over consolidated clay. So if you have normally consolidated clay means it's just like loose sand because you have not compacted previously. You have not applied consolidation previously, right? But for over consolidated soil, what will happen? It is something like dense sand. We already made the compaction and then only we apply these uh, additional forces like shear forces. Okay, right? So now if we have two different soil samples for dense sand and loose sand, so this will be the behavior. You can see y-axis, it is clearly mentioned over here. Y-axis is tau, x-axis is shear displacement. So I have made two graphs. One is for dense sand or over consolidated clay. Blue line is for loose sand or naturally consolidated clay, right? Normally consolidated clay, over consolidated and normally consolidated clay, right? In those two situations, right? So the graph behavior you can see. So over consolidated clay, the shear strength value is always is in most cases it is higher than normally consolidated clay. That is one of the observation. I repeat, the shear strength value, tau F value of over consolidated clay is higher than uh, the shear strength value of normally consolidated clay. And the other thing, other important behavior you can see in over consolidated clay, once you increase the shear displacement, shear distress will be increased up to a certain point. After that, it will be decreased and available to a constant value. But in normally consolidated sand, what will happen? It will be gradually increasing because it is already loose, right? It is normally consolidated clay. Okay. So those are the things that you need to focus. The other thing, in case of over consolidated clay and normally consolidated clay, once you apply the shear displacement, we are now seeing change in height of the sample, right? Once you apply the shear displacement, what would be the change in height of the sample, right? So in that situation, you can see the over consolidated clay, it has a drop or it has a compression at the very beginning and it changes its change in height as expansion, right? But in case of loose sand, the change in height will be negative and it will be keep aggregating, keep increasing, and it has a certain compression, right? Okay. Now, now we discuss about direct shear test on dry sand, means loose sand or dense sand, or over consolidated clay, or naturally normally consolidated clay. So now direct shear test on clays, right? In case of clays are available, what would be the direct shear test uh, result? The horizontal displacement applied at a very slow rate to allow dissipation of pore water pressure. One test would take several days to finish. Now, compared to dry sand, uh, compared to normally consolidated clay, the other clays requires kind of high duration for direct shear test. But if you get the dry sand, it will not take much time. Sometimes only 1 hour, 2 hours, something like. But in case of clays where the soil is having different soil fine particles are available, so in that situation, it will take time. Sometimes uh, several days, right? Sometimes 1 week, right? Likewise, it depends on the type of soil. Okay. Failure envelopes of clay from drain shear test, right? So these are the failure envelopes from drain shear test, right? So we have normally consolidated clay and over consolidated clay. You see the difference. Normally consolidated clay, it's always goes under the origin, right? It's like y equals mx type curve. But in situations like over consolidated clay, it's not going through the origin. It has an intercept, right? So C is not equal to 0. Now, in normally consolidated clay, C is equal to 0. That's why no intercept will be there. It goes through the origin. But when it comes to the over consolidated clay, you can see there's a intercept in the graph. So that C is not equal to 0. Okay. So these are the advantages and disadvantages of direct shear test, right? We will go through one by one. So this test is simple. That is one of the advantages. And it is very easy test. And it will not take much time. It is quick. Interface strength parameters can be determined. What I said previously, so this direct shear test, we allow the soil sample to fail under predetermined surface. So our predetermined surface is this one, right? So the results coming from F will give you the shear strength value along this surface, right? Along this surface. So that means we are determining shear strength parameters for a given and known surface, right? So if you want to calculate the shear strength along given surface, you can um, carry out this, right? So now the advantages are it's really simple and quick, right? Compared to the other testing, it's really simple and quick, and also interface strength parameters can be calculated. But in case um, the direct shear test, since we are now determining the interface shear strength parameters, it may not be the correct shear strength of the given soil because there may be some other weaker planes. Okay. And the disadvantages are failure occurs along a predetermined failures plane. So that is one of the key disadvantage. And the area of sliding surfaces changes as the test progresses. Non-uniform distribution of shear stress along failure surface. Reliable mostly for granular soil. Okay. So there are certain advantages and there are certain disadvantages. So you may understand these things. Those are very minor. Anyway, for this one, area of the sliding surfaces changes as test progresses. So hope you can remember. I discussed last time also. So this is the shear box. Okay. So once you move the bottom surface, so this length is delta H. Also, we have this delta H as well. So when you deduct, you have to deduct 2 times delta H. Understood? So each side you will have shift, right? So if you shift this entire plate, there will be delta H in this side and also there will be delta H on this side. So what is the touching length then? Let's say your length is L from here to here. So only the touching length will be calculated with shear strength, no? So that L minus 2 into delta H. Okay. That would be the touching area. Okay, no? So that's why once the test is progressing, this delta H value is getting increased. So that area of the sliding surface changes. Frequently it is changing. When the test progress, it changes. Non-uniform distribution of shear stress along the surface. Because you apply the force over here, right? You apply the force somewhere here. Once you apply the force somewhere here, you cannot say the shear stress is equally distributed along the surface. Not possible. You cannot say like that. So that what will happen, the shear stress will be concentrated around the applied force area and it will not be distributed evenly. And somewhere here, it has less amount of shear stress mobilized. So throughout the surface, the shear stress will not be distributed equally. That is one of the disadvantage. And reliable mostly for granular soil. As I say previously, for granular soil like dry sand, it is this test is very much and very much easy, right? Because as I said, in dry sand, what will happen? The granular soil, right? The shear strength will not be depend on the cohesion, right? Cohesion is the particle bonding. As you know, there's no bonding in case of dry sand is available to you, right? So because of that thing, cohesion will not be considered. It is zero always, right? Okay. So let me discuss about angle of repose as well. So angle of repose means now in case you have a soil, so if you want to stockpile the soil, so you cannot make it right angle, right? You cannot uh, stockpile the soil like this, right? So this is your stockpile. You cannot make a stockpile like this because these sides will be collapsing. So there should be a certain angle. So if you made a certain angle, if you maintain a certain angle, this side can be maintained without collapsing, right? So that angle, this angle we say angle of repose. Okay. So this angle of repose, it is a clear example like this. There's a soil stockpile. So in that situation, we are making angle of repose, right? So that this side will not be collapsed without and it is remaining as it is, no collapsing. Okay. So the important part is this angle of repose is more or less equal to the friction angle of the given soil. Okay, right. So with that, we come to the conclusion of direct shear test. Do you have any problems? If so, please raise now. If not, we will move to the unconfined compression test. If you have any question, please let me know. I will give you two minutes. Any questions regarding direct shear test? Or do you want me to explain something additionally or any clarifications regarding the things we discussed here? If you don't have any problem, shall we proceed? Nobody is speaking. Any question from direct shear test or things we discussed so far regarding the shear? If there's anything, please let me know. If not, we will move on. Okay. Right? We will move to unconfined compression test. Right? What's the meaning of unconfined? Unconfined. Unconfined means it is not confined. It is not confined. Means it is not kind of protected from its surrounding. It is not protected from its surrounding. Right? So it will be like this. We will prepare a undisturbed soil sample and then without having a cover, without having certain kind of confinement, we will test the soil sample as it is, right? The soil sample will be placed on the test equipment and then we apply the vertical stress. No horizontal stresses will be generated, right? And then we let the soil sample to fail on its own discretion, right? And then we calculate what is the shear strength of this soil sample. That is the unconfined compression test. Very simple. We keep our soil sample without having a cover, without having a confinement, and then we apply the soil stress and let the soil sample to fail under its own weaker surface, right? So that once the failure is occurred, we calculate what is the stress, right? We calculate what is the vertical stress for failure, right? Okay. So moving on. So similarly, as we said short while ago, the any test, this equation valids. So now tau f is equal to C plus sigma tan phi. So what happened here? We do not have any vertical stress. Sorry, we do not have any horizontal stress. Instead, we have the vertical stress only. So the confining pressure, the horizontal force will be 0. Sigma 3 will be 0. Only sigma 1 is available. Okay, this is a kind of failed soil sample. You can see clearly it has been failed on its decretion, right? On its own idea, on the soil sample's own idea, it has been failed, right? Okay, right. So let's talk about the stress behavior, stress and strain behavior. So as you can see, once the soil has been loaded, right? Once the soil has been loaded, what will happen? There will be certain strain also. It will be made available. So once the stress is increased, strain will also be increased up to a certain maximum value. And then it will be reducing, and later it will be continuing on the constant value, right? So means even though the strain increase, stress will not be increased. සොයිල් සාම්පල් එක කැඩි 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 යනවා. සොයිල් සාම්පල් එකේ ස්ට්‍රේන් එක වැඩි වෙනවා කියලා කියන්නේ මොකද වෙන්නේ? එයාගේ වොලියුම් එකට සාපේක්ෂව එයාගේ ඩිෆෝමේෂන් එක වැඩි වෙනවා. ඒ කියන්නේ මොකද වෙන්නේ? එයා කැඩි කැඩි යන්න බලනවා. නමුත් ස්ට්‍රෙස් එක වැඩිවීමක් වෙන්නේ නැහැ. මුලින්ම වෙන්නේ ස්ට්‍රෙස් එක වැඩි කරගෙන යනකොට ස්ට්‍රේන් එකත් ඒ හා සමානව වැඩි වේගෙන යනවා. එතකොට ස්ට්‍රෙස් එකේ මැක්සිමම් වැලියු එකක් එනවා. ඒ වැලියු එකෙන් පස්සේ ස්ට්‍රෙස් එක ස්ට්‍රේන් එක වැඩි වෙනකොට ක්‍රමක්‍රමයෙන් අඩු වෙලා යම්කිසි නියත වැලියු එකකට එනවා. නිශ්චිත වැලියු එකකට එනවා. Okay. So this the maximum stress we observe, we say as QU, that is equal to unconfined compressive strength. Unconfined compressive strength. Okay. So how to determine this unconfined compressive strength? It is this way. First, this is the same graph which we discussed short while ago. That is QU is equal to sigma 1. Now we are going to evaluate how to determine C and phi for this, right? So as you can see, in this situation, sigma 3 is equal to 0, sigma 1 is more than 1. It is more than 0. So in that situation, so how to draw the Mohr circle? Sigma 3 is 0, means it is somewhere here at the origin. And sigma 1 will be positive value. It will be like this, so that the Mohr circle will be drawn as per this figure. Okay. So our Mohr Coulomb failure surface will be a tangent to this, right? So since it is touching here, you cannot have inclined tangent to this one. Instead, what will happen is there will be certain uh, failure line like this, right? So the failure will be totally depend on CU. That means, right, intercept cohesion value of the given soil. So as you can see, CU is equal to tau F. Tau means, as we discussed, it is sigma 1 divided by 2. How it comes? This is the circle. Here we have sigma 1. So that the um, diameter of this circle is sigma 1. How about the radius? Radius will be sigma 1 divided by 2. So that's why the height from here to here, that will be the tau value, will be sigma 1 divided by 2. Okay. So QU, sigma 1 is equal to QU, CU is equal to QU divided by 2. Okay. So phi value on the other hand, since there will be a horizontal line, no slope will be there. So that's phi value will be 0. And undrained cohesion, Cu is equal to undrained strength or tau F value. Cu is equal to tau F value. Okay, right. Hope you understood. Now we will have a short break. After that, we will come to this slide to discuss about the triaxial testing. Okay, we will have a 10 minutes break, and after that we will meet. Okay, we will now continue. Mm, Now we are going to discuss about the triaxial test. We discussed about direct shear test. We discussed about unconfined compression test. Now we are discussing about the triaxial test in detail, right? So as I said previously also, this is the normal site condition, right? So they are, as you know, if no civil structure is constructed over there, if you consider a soil point below the depth is said, there you can see the horizontal stresses have been applied and the vertical stresses have also been applied. So once you construct something, let's say foundation, the vertical stress will be increased. So the same stress conditions we have to apply to the lab conditions. Then only our results will be valid. Whatever the whatever the physical conditions available at site, it should be made available in laboratory testing. Then only your lab results will be valid. Okay. So now for triaxial test, as I said, the physical conditions, right? We apply to the test condition so that we will apply certain horizontal stresses and then vertical stresses will also be applied. And after that, what we will do is we further increase the vertical stress until the failure. So the failure will be happen on the determined surface by the soil on, not by us. It will be decided by the soil, right? The soil will decide, okay, what is my weakest soil plane? Along that, I will fail, something like that. So that is the triaxial testing, okay? In the triaxial test, mm, we overcome certain disadvantages which we observed in direct shear test and unconfined compression test. UCCT means unconfined compression test. DST means direct shear test. So what are the advantages over DST and UCCT? This is more versatile. Drainage can be well controlled. As you know, soil we have water as well. Poor water as well, uh, we can observe pore water, right? So when the soil water is there, what will happen? The shear strength capacities, shear strength capabilities will be changed. So in direct shear test, we do not have such kind of provision to provide this drainage conditions. But in triaxial test, we have such conditions to maintain. So it is we can make the lab conditions and we can simulate the lab conditions with the real life conditions, right? So that drainage can be well controlled. No rotation of principal stresses like direct shear test. Failure plane is the weakest one. So those are the advantages. Field stress conditions can be replicated through confinement. Okay. Now let me show you the triaxial test apparatus and we will discuss the principle and the test method, how to do the testing. Okay. Now triaxial compression test. Here we have a soil sample. This soil sample will be placed inside the cell, right? Cell එකක් ඇතුලේ තමයි මේ soil sample එක තියෙන්නේ. This cell will be filled out of water, right? So this water, the water pressure can be controlled by different valves over there, right? Different valve over there, so that we can control the cell pressure, the water pressure inside. Okay, right? And we have this soil sample over here. Connected to this soil sample, we have several um, drain lines as well. So the water can be passed through the soil sample through these drain lines. Okay. On the top and the bottom, you have several pipes available. So from these pipes, our the water inside the soil can be controlled. Okay. And the other thing is, to give the vertical stress, we have a shaft connected there, so that we can apply the certain vertical stress onto the soil sample. So there are few provisions. I repeat once again. First thing is cell water pressure. Inside the cell there is water. So we have certain provision to uh, to control the water pressure inside. So that is one of the provisions. The other provision is the soil has been connected with several drain lines so that water can pass through the soil. So the pressure built within the soil through the pore water can be controlled with these drains. Okay. And we have a vertical shaft over here. So that vertical shaft will give you a deviator stress or the vertical stress over there. So those are provisions, right? The realistic apparatus is provided there, right? You may see these things in your previous studies. So now the field conditions are, as I said previously, certain horizontal stress and vertical stress are available without the foundation, right? Once you construct the foundation, what will happen? Certain vertical stress additionally applied, right? Horizontal stress, no change. Vertical stress has been additionally applied. So we say this delta sigma as deviator stress. The stress deviated, the stress increased. So that we called as deviator stress. Deviator stress. Okay. So now the normal stress. Now we have several figures over there. Now the triaxial compression test will be made like this. As I said, the soil sample is kept in the triaxial test and it will be filled inside the cell. The cell will be filled by the water. This water will be pressurized through these valves. So once the pressurization happen, the stresses coming from the water will be applied on the soil sample. Let's say the cell pressure is 150 kilonewtons per square meter. In that situation, the soil will be subjected to water pressure of 150 square millimeter. Okay, 150 kilonewtons per square millimeter. So it applies in all direction, horizontal, vertical, incline, in whichever direction it is, it applies the same stress. So that's what I mentioned, sigma 3 around this soil sample. You can see vertical stress also sigma 3, horizontal stress also sigma 3. What is the real meaning of this one? Our first step would be the cell pressure. Cell pressure is the water pressure. Water pressure is applied equal in every direction, vertically, horizontally. That's why sigma 3, cell pressure is applied in horizontal direction and the vertical direction. Okay. And as I said you, now our first step would be cell pressure. The field condition we have to maintain. Let's say the horizontal pressure, vertical pressure available at site, right? Available at site here, sigma h, sigma v. Let's say it is 150 150 newtons per square millimeter. So in that situation, what we will do is 150 will be applied from this cell pressure. Okay. And then as a result of this foundation construction, let's say certain additional stress has been applied 100 kilonewtons per square millimeter. So in that situation, we will apply 100 kilonewtons per square millimeter from this deviator stress only in the vertical direction. No horizontal force will be applied, only the vertical force will be applied. That is the implication of foundation loading. Okay, understood? So the simulation will be like this. Sigma 3 will be applied in all direction by using the cell pressure. And then we will apply the deviator stress. So with the deviator stress, we have sigma 1 is equal to sigma 3 plus deviator stress. And horizontal pressure will be kept remained as it is as sigma 3. Okay. So the normal stress sigma 1 will be the confining pressure plus deviator stress. Sigma 1 is the major principal stress. Sigma 3 is the minor principal stress. And the deviator stress will be applied. The meaning is sigma 3 will be the minor principal stress. Sigma 3 plus sigma 3 plus Q or sigma 1 will be the major principal stress. Clear? Sigma 3 cell pressure එකෙන් apply වෙනවා. අපි වැඩිපුර දෙනවා foundation load එක simulate කරන්න sigma 1 sorry Q දෙනවා වැඩිපුර. sigma 3 අපි already මෙතන තියෙන cell pressure එකෙන් ඊට අමතරව අපි Q දුන්න හින්දා deviator stress එකෙන් මෙතන දැන් simulate වෙලා තියෙන vertical load එක sigma 1 simulate වෙච්ච horizontal force එකේ කිසිම වෙනසක් නැහැ horizontal stress එකේ ඒක cell pressure එකෙම maintain වෙනවා. එතකොට දැන් final condition එකේදී sigma 3 horizontal තියෙනවා. sigma 3 plus Q තියෙනවා vertical. sigma 3 plus Q තවට තමයි අපි කියන්නේ මොනවා කියලාද sigma 1. sigma 3 plus Q is equal to sigma 1. වෙනත් කතාවකින් කියනවා නම් major principal stress එක කියලා කියන්නේ. ඒ කියන්නේ sigma 1 නේ. major principal stress එක කියන්නේ sigma 1 මේ direction එකේ තියෙන එක. ඒක සමාන වෙනවා minor principal stress එක sigma 3 වලට එකතු කරා නම් හරි deviator stress එක sigma 3 plus Q. Okay? තේරෙන්නේ නැති. right තේරුම් නැත්නම් අහන්න මොකද මින් පස්සේ අපි calculation කීපයකට යනවා සහ exam එකේදී ඔයගොල්ලන්ගෙන් මේකේ ප්‍රශ්න ගොඩාක් අහනවා. ඒ හින්දා මොනවා හරි තේරෙන්නේ නැත්නම් තියෙනවා නම් කරුණාකරලා අහන්න. හරි? ප්‍රශ්න නැත්නම් අපි ඉස්සරහට යමු. මොකද මේ ප්‍රින්සිපල් එක තේරෙන්න ඕනේ ප්‍රශ්න වලට යන්න. ප්‍රශ්න මොනවා හරි තියෙනවද? උදේශිකා
Yes,
Gayatri
sir.
clear?
Yes, sir.
Okay, right. So now we are moving to the triaxial test and it's the indication of the test results, discussion of the test results. Now, as I said you, this is the cell is filled out of water. So you can see once we apply the deviated stress, the failure has been occurred. So if the failure is developed like this, you see it is inclined surface. We say this is the shear failure. But in some situations, failure can be happen in this direction as well, like bulging. It has been bulged. So in that situation, the test result cannot be obtained or cannot be assumed for the shear principle. We have to check what is the formation of the failure. Okay. Now, x direction axial strain, y direction deviator stress. So this is the behavior. So you can say once the strain is increased, deviator stress will also be increased, right? Up to a certain value. So this is the maximum deviator stress once you increase the axial strain. So we say this one deviator stress at failure. After the failure, when you increase the axial strain, deviator stress will be reducing, and finally it will be come to a certain constant value. Okay. So similarly, like our previous situation, if we increase our confining stress, right? If we increase our confining stress, what will happen? The deviator stress required for the failure will be getting increased. I repeat, if you increase the confining stress, now let's say you are doing the 3 tests for one sample, right? One soil, you will do 3 times test. In first test, you will be having a lower confining stress value. Second test, you will increase the confining stress. Third test, you will again increase the confining stress. Let's say here 100, 150, 200. Once you increase the confining stress and do the triaxial test, your deviator stress at the failure, your deviator stress at the failure will also be increased, right? So for the lower confining stress values, the deviator stress versus axial strain, the curve will be like this. So the maximum value will be somewhere here. Once you have the higher confining stress, the deviator stress will be somewhere here. That would be the maximum value. So failure, right? And then once you have the highest confining stress, again, your deviator stress at failure will be somewhere here. After that, the deviator stress will be lowered and make it constant. So the failure will be occurred at this situation. So you see, the deviator stress at failure, it has been getting increased once you increase the confining pressure. That is one of the observation. The other observation is, if you maintain the lower confining stress, the cell pressure, if you maintain the lower cell pressure, it requires higher axial strain for the failure. You see, the axial strain for the failure is somewhere here. But when you increase the cell pressure, the failure occurs at lower strain values, right? The second sample strain will be at this point. Third sample, where the highest confining pressure is there, in that situation, lower axial strain will be there at the failure. Okay. So those are the observations in these curves. Hope you understand. Right? So now we have shear stress and the sigma value. So this is the shear, this QFC is the deviator stress. So if you draw sigma 1 and sigma 3 value, right, for 3 samples. So this is the first sample. In the first sample, QFA, that is the deviator stress value. So since you know the confining stress value sigma 3A, you can draw the sigma 3A, and the diameter would be QFA, so the deviator stress, and then this one will be the major principal stress. For the second sample, you know the confining stress sigma 3B. You know the diameter as well. Diameter is QFB. You know QFB, you mark, and then you will get the sigma 1B, so that you can draw the Mohr circle. For the third case, you know the confining stress sigma 3C. You can mark over there, and then you know the deviator stress at the failure QFC. So that QFC you can mark from there onwards. So that is the deviator stress. So that you can mark the major principal stress at this point and draw the Mohr circle, right? So common tangent will give you the failure line. Okay. so that you can determine C and phi value of the given soil sample. Understood? At least three testing should be done. At least three testing should be done so that you know sigma value. I am moving little bit further in triaxial test, right? So actually, we have several triaxial tests, right? You may know these things, but I am giving you a kind of reminding session, right? In the triaxial test, we have two steps, right? As you know, we are having sigma C. So we are having cell pressure, right? And also, uh, once you apply the cell pressure, as you know, I will show you one. This is the triaxial apparatus. Once you apply the cell pressure, if your drainage valves are open, what will happen? These drainage valves are open and you increase your cell pressure. What will happen? Once you increase the cell pressure, your soil sample will be compressed, right? So if your soil sample compressed, soil particles will be compressed. Also, water inside will be compressed. So if the water will be compressed, what will happen? Water tries to evacuate. Water tries to go away from the soil. Now your drainage valves are open. In that situation, what will happen? Soil can easily pass their water outside. So this is something called consolidation. Once you apply the pressure, if the water pressure can be released easily, in that situation, we say it is a consolidated soil, right? Let's say your drain valves are closed. Your drain valves are closed. Then you increase the cell pressure. What will happen? Again, same thing happen, no? Soil sample will be compressed. Soil try to remove its additional pressure using its water, right? Water tries to remove its pressure. Water tries to dissipate its pressure. But the valves are closed now. So in that situation, what will happen? Water cannot remove its additional pressure. So it is a kind of unconsolidated situation. Okay. And the other thing, now we discussed about cell pressure. Other thing, the deviator stress. Once you apply the, now cell pressure is applied, okay. We can check whether the valves are closed or not, right? So that we can determine this is simulating with consolidated condition or unconsolidated condition. So after that, we apply the deviator stress. Now again, what will happen? The water inside the soil will be additionally compressed. Let's say the valves are closed over there. So in that situation, what will happen? As a result of this deviator stress, now the water has been compressed, but water tries to remove its pressure. It is not possible, right? Because the valves are closed. So drainage is not possible now, right? And let's say once you apply the deviator stress, if the valves are open, so in that situation, the soil can pass its additional pressure due to this deviator stress, so that drainage is possible. Okay, right? The simulation would be like this. So we have two steps. The first step would be the cell pressure. Second step would be the deviatoric stress. So as you know, once you apply the cell pressure, the water inside the soil sample will be compressed, right? If the drain valve is open, what will happen? This additional increased water pressure will be released. If the drain valves are open, you can see, if the drain valves are open, yes, then it will be a consolidated soil sample. If the drain valves are not open, that means it is unconsolidated soil sample, means this additional stress in this water due to the cell pressure cannot be released since the drain valves are not open. Okay. On the other hand, once the deviatoric stress is applied, what will happen? Again, the soil sample, the water will be getting compressed, right? So if the drain valve is open, so drain conditions can be applied, right? If the drain valves are not open, the undrained conditions will be applied. Why I discuss this one? The reason I want to discuss with you the triaxial testing types, right? Okay. So now step 1, we have consolidated, unconsolidated. Step 2, we have drain, undrained. So we combine these situations so that we will have consolidated drain condition combined together so that CD triaxial test. Unconsolidated sample and undrained situation, we will have UU triaxial test. Then we have consolidated undrained condition, CU triaxial test. So we have 3 types of triaxial test: CD triaxial test, UU triaxial test, CU triaxial test. Okay, right? There are 3 types of testing. Now you understand what is 3 types of triaxial test, why we have these conditions, so that now in physical life, in your actual life, the soil conditions can be either of this form, right? Sometimes we have consolidated soil, but when you have the additional loading, right, it it has sufficient time to drain the water due to this additional loading, which is CD test will be applicable. So sometimes we have the unconsolidated soil will be there, and once you apply the deviator stress, we don't have sufficient time to drain the water, so that UU test will be applied. So all physical conditions can be simulated with these triaxial tests. Okay. So now I am going to discuss with you some of the practical applications for triaxial tests, right? First one, CD test, right? So let's say now there's an example. The soft clay layer will be there, okay? For a long time, it was there. So we can say the consolidation already happened. Soft clay was there for a long time. So that means consolidation already happened. And now you are going to construct the earth embankment over there, but very slowly. You applied the first layer, kept it for certain higher time, and then make it compaction and kept for certain time. Let's do the second layer, keep it for a kind of additional time, and after compaction also you keep for certain time. Like that, you will take huge time to construct the embankment. So that means as a result of this embankment, certain uh, additional stress can cause in the soil, soft clay, right? So, but since it is constructed very slowly, what will happen? There's a sufficient time to drain the additional pressure. Okay. Previously, soft clay was there. for a long time. It's already consolidated. And also new construction of embankment will do in very slow speed, right? So you can say if somebody asks you to check the soil stability, so the shear strength of the soil in this soft clay, what is the preferable test? You have to use CD test. CD test. Consolidated drain triaxial test. Okay, understood. The other thing, let's say uh, now there's a earth dam, right? And a certain steady seepage will be there, right? Certain steady seepage will be there. Already seepage is there, right? Earth dam was also there for a long time, and the seepage is also it is very steady. So that means since the earth dam was there for a long time, consolidation already happened. And steady state seepage happen means the draining also happen properly. So that if somebody asks you to uh, determine the shear strength value of this core material, then you have to use the CD test. So in summary, CD test simulates the long-term condition in the field, right? Long-term conditions. Consolidation also happen in a long time. Draining also happen in the long time. So that CD test simulates the long-term condition in the field. And CD and 5D used to evaluate the long-term behavior of soil. Okay, understood? Now, with that, we will move to CU test, right? Now, let's say CU means what? Consolidated undrained triaxial test. Okay, consolidated undrained. Let's say soft clay. The previous example, soft clay layer was there for a long time, means the consolidation has been taken place. And we construct the embankment rapidly. First layer, okay, compacted. Next day, second layer, compacted. Third day, next layer, compacted. So the rapid construction, right? So whatever the additional stress coming from the embankment can generate additional stress in the water inside soft clay layer, right? So as a result of this additional loading, water will be compressed in soft clay, okay? But it doesn't have sufficient time to release its additional pressure. Draining is not possible, right? Because the construction is happened rapidly, okay? So that if somebody asks you to calculate the shear strength value in the soil, soft clay, what would be the test you will select? You have to select CU test, consolidated undrained triaxial test, CU test. Okay, hope you understand now, right? So let's say a dam is there for a long time, King's time. During the King's time, this dam has been constructed. Let's say there's a rapid drawdown. Let's say the water level has been rapidly gone down. So in that situation, what will happen? The water will be saturated here, but it doesn't have sufficient time to release its additional water pressure over here. So as a result, this earth dam can be failed. So if somebody wants to calculate the shear strength of this core, what would be the best test for this one? Since the consolidation already taken place, it may be CD or CU. The drawdown or the lowering of the water level has been happened rapidly. So as a result, you have to go for this undrained condition. It doesn't have sufficient time to drain. right? Okay. Now we come to the last test, that is UU triaxial test. So in UU triaxial test, what will happen, right? Unconsolidated, undrained, right? Let's lay soft clay layer we will have, but it is unconsolidated. It is not consolidated. So certain additional stress, it is yet to dissipate, right? Certain additional pore water pressure, it is yet to dissipate. Even with this condition, we will construct the embankment rapidly. What will happen? It is the soft clay layer is still in unconsolidated situation. In addition, certain additional pressure will come from the embankment as a rapid construction, right? So unconsolidated situation is there. As a result of rapid construction, there's no time for the draining. So undrained situation. So we say, if somebody asks you to determine this the shear strength of this soil, what you have to do is UU triaxial test. UU triaxial test, or else unconsolidated undrained triaxial test. Okay. And let's say we are going to construct a, a dam, like large dam, right? And no change in water content of soft clay, right? We construct a dam rapidly. Also, there's no time to drain water, right? So, since the construction is done rapidly, no time for the consolidation and no time for the draining. So, what you have to do, UU triaxial test, if somebody asks you to do the shear strength calculation. Okay. So there are many practical examples for each type of triaxial testing, so that I hope you get a clear idea which test to be used for which case. Okay. So there's a note here. UU test simulates the short-term condition in the field, means the rapid conditions. No time for consolidation, no time for draining. Even UU triaxial test will not take much time for to do at the laboratory. But if you want to do the CD triaxial test, it will take much time to conduct in laboratory, right? UU test in laboratory also, it will not take much time, right? UU can be used to analyze the short-term behavior of soils. The short-term behavior can be determined by UU triaxial test. Okay. So with that, my presentation today will be finished, right? So we have 1 hour more. Let's have a session, a kind of uh, some of the classroom activities, right? For shear strength. Right. Do we want a break or shall we continue? After break, or if we continue now, what's your point opinion? Shall we continue or we will have a break and continue? Udeshika, Madhushani, Udeshika. Hmm? Shall we continue or we will have a short break and continue? Because we are now going to do some classroom activities. I want you to prepare with a paper and a pen. Okay. So we will have 5 minute break. Please bring kind of paper and a pen. We will have a classroom activity within the balanced time for shear strength of soil. So we will have 5 minute break, and after that, please come to the session with a piece of paper and a pen. Okay, thank you. Okay, I hope you come with a paper and a pen. Okay, now we are moving to the last session of today. So shear strength, we are now going to start classroom activity. Okay, right? So our question number one, a sample of saturated clay is subjected to an unconfined compression test, right? A sample of saturated clay is subjected to an unconfined compression test. As the sample fails at a pressure of 40 kilopascal, that is to say, its unconfined strength, compression strength, QU is 40 kilopascal. Determine the soil's undrained shear strength, right? Soil's undrained shear strength you have to calculate. So now we have certain things we have to you have to understand here. A sample of saturated clay, a sample of saturated clay, right? So it is subjected to an unconfined compression test. So that is the second test we discussed, right? So the sample fails at the pressure of 40 kilopascal, right? So QU is equal to 40 kilopascal. So what you have to determine is soil undrained shear strength, right? Hope you all can remember unconfined compression test, right? Right now we are going to calculate like this. The unconfined compression test is a special type of compression test with no radial stress is applied to the sample. That means sigma 3 is 0. Hope you all can remember, right? In the unconfined compression test, unconfined. No confinement is there. Sigma 3 is 0. Consequently, the test is only suitable for soils capable of standing by themselves without lateral support. That means cohesive soil. It is also commonly employed in rock mechanics practice. Ordinary, the principal stress and the cohesion would be related by. So this is our equation. Hope you all can remember the week before last week, we discussed about this equation. The correlation between, right, sigma 1 and sigma 3 and phi c. Okay, phi c and sigma 1 and sigma 3 value. So now here, sigma 3 happens to be 0 because no confinement load will be applied. No horizontal load will be applied. So that this sigma 3 value becomes 0. And this is a cohesive soil. If it is cohesive soil, phi value becomes 0. Cohesive soil no, right? Cohesion එකක් තියෙනවා නම් ගොඩාක් ලොකු cohesion එකක් තියෙන soil එකක් තමයි මේකට පාවිච්චි කරන්නේ. ඔයගලන්ට මතක ඇති අපි මොකද්ද මේ එක more circle එක ගැහුවාම ඒ more circle එක මෙන්න මේ විදියට. Hope you can remember for unconfined compression test, more circle came like this. Because sigma 3 value is 0 and sigma 1 value will be somewhere here. And this is how we draw the failure envelope, where phi value becomes 0. So that is the most important judgment in unconfined compression test. Sigma 3 is 0, phi is equal to 0. So if you substitute these values to this equation, the entire part of this part will be 0. And since phi is 0, here we will have only tan 45. Tan 45 is equal to 1. So sigma 1 will be equal to 2c, right? So the c value will be sigma 1 divided by 2. As you know, sigma 1 value will be QU. QU is given as 40 in the question. 40. QU is 40. So if you know QU value 40, 40 divided by 2, the answer will be 20. So unconfined compression, undrained shear strength will be 20 kilopascal. So this kind of question also expected in your exam paper, right? So in unconfined compression, if somebody asks you to determine the shear strength or something like that, there your main judgment should be sigma 3 is 0, phi is equal to 0. And just apply to the equation so that you can determine the shear strength value, right? Okay. Question number 2. An unconfined compression, again unconfined compression test, was carried out on a saturated clay sample. Maximum peak loading the clay sustained was 134 newtons and the vertical displacement was 3.8 millimeter. The size of the sample was 38 millimeter diameter and 76 millimeter long. Determine the undrained shear strength, right? Determine the undrained shear strength. Now, can you calculate this one? Huh? Maximum loading is there. Also, sample diameter is there, sample height is there, and vertical displacement also given as 3.8 millimeter, right? You are asked to calculate and determine the undrained shear strength. Okay, right? First, note here, the sample has been failed, right? The maximum loading is given as a load 134 Newton. This is not a stress. So you have to note that, right? Since it is given as a load, you have to convert this to the stress. How to convert the force into stress? Very simple. Force divided by area would be the stress. Okay. So you know the force. Now you need to determine the area. How to know the area? It's very simple. 5d square divided by 4. D is the diameter. So diameter is given in the question, that is 38 millimeter. You just substitute here. So the value would be 1.13 into 10 to the power minus 3 square meter. So that would be the area of the sample. So now note that your loading has been applied over this area. But actually what happened, right? This is the soil sample. So this is the unconfined compression test, okay? So the area would be this one. This is the area. But what happened during the loading, this area has been gone down. The volume has been, the height has been reduced. There's a vertical displacement, right? Certain vertical displacement over there. If the vertical displacement is there, what will happen? ඔයාගේ යම්කිසි බරක් ඇප්ලයි කරනකොට ඔයාගේ සාම්පල් එක පහක් වුණොත් ඒ කියන්නේ මොකද්ද? ඒරියා එක අනිත් පැත්තෙන් වැඩි වෙනවා. right? ඒ කියන්නේ ෆෝස් එක ඇප්ලයි වෙලා තියෙන්නේ මේ ඒරියා එකටද? ඇත්තටම මේ ඒරියා එකට නෙවෙයි. එහෙමනම් ඒක ඇප්ලයි වෙලා තියෙන ඒරියා එක ඔයා කැල්කියුලේට් කරගන්න ඕනේ. So that's how you do this, right? So the vertical strain sigma epsilon 1 will be given as what would be the epsilon 1? Delta Z, that would be the vertical displacement divided by H naught. H naught is the initial height. So delta Z is equal to 3.8. H naught is 76. So the epsilon 1 would be 0.05. Okay. So then, so this is the equation for to calculate the new area. A naught is the initial area, 1 minus this one. This is the epsilon 1, vertical strain. So the final area would be 1.19 into 10 to the power minus 3. Now you know PZ, right? PZ is 134 and the new area is 1.19 into 10 to the power minus 3. So that sigma 1p applied vertical stress is 112.6. So undrained shear strength is what? Sigma 1 minus sigma 3 divided by 2. Here sigma 3 not available. No confined pressure is there. Unconfined compression test. So that sigma 1 divided by 2, the final answer would be 56.3. Okay. So this time you can expect a question like this in your exam paper, right? I will tell you the force at the failure, an initial diameter, and the vertical strain. Everything will be there in your exam paper, so that you need to calculate the shear strength and undrained shear strength. Okay. So you can expect a question like this. And the question number 3. So now direct shear test. Okay. Direct shear tests were conducted on a dry sand. The sample used in the test had a square base area of 5.08 centimeter into 5.08 centimeter and a height of 1.905 centimeter. The test results are provided below. Determine the shear strength parameters C dash and phi dash. So normal stress, normal load is there. Shear force at failure is there. In newtons, what you have to do is shear strength parameters you have to calculate. Right? So now the load is given. So normal load is given 66.72. Likewise, several uh, loading is there. And the corresponding shear force at failure also given to you. Right? So now how to calculate? How to determine the shear strength parameters C dash and phi dash in the question. Okay. Huh? Can somebody help me? In this group, nobody is talking. I mean, they keep silent. Last time there was not like that. In your previous batch, many people discussed with me during the class, and it was very convenient for me. If somebody had the interactive session, it will be very beneficial to the audience and also to the lecturer. So anyway, this time nobody tries to speak and nobody tries to have a interactive session. That's very lacking, right? Anyways, now if you know the normal load, if you want to calculate the normal stress, what you have to do is, now this is direct shear test. Hope you all can remember. So this is the sample apparatus. Okay, it is like this. Okay, and then this is the lower box and upper box. Lower box is subjected to certain pressure, certain load. So that's what mentioned here. And then that's what mentioned the shear force at. And the normal load will be applied on this top, right? So that's what mentioned in this normal load. Okay. So if you want to calculate the stress, what you have to do is force divided by area. What would be the area? The base area. Base area is given in the question as 5.08, right? 5.08 into 5.08. So that very easy, normal load divided by this area and convert that to meter square, so that newtons per meter square you can get the result. Shear force also, now shear force will be applied on this surface. So the surface area, again it will be the base area. Since no indication of the shifting is mentioned, you can remain on this area and calculate. Okay, right? The soil is a sand, so C dash is 0. In the question, it is clearly mentioned it is a dry sand. So if it is dry sand, no cohesion is expected. If no cohesion is expected, C will be 0. And the cross-sectional area, as I said you, 5.08 centimeter into 5.808 centimeter. So the answer would be 25.8064 centimeter square. So if the normal load like this, normal stress can be calculated as this shear force divided by this area will be, the shear stress will be like this. 80.07 divided by 25 will be this one, because you get it in pascals. Pascals mean you convert this to square meters. So if you convert this to square meters and divided from 80.07, the answer would be 3106.4. Likewise, you can calculate for the remaining values, right? Okay, and then you have a graph where x-axis is normal stress, y-axis is shear stress. And once you draw a graph, the graph values and the graph values will be these. Pascals 2584.8, 2068.3, like that you mark, right? And every value will give you certain uh, point, right? Accordingly, the best suiting curve you can mark. That would be the failure envelope. So if you get the gradient of this one, that would be the phi value. Gradient would be 0.7829. So that this will be the tan value. Then tan phi would be this one. So the phi value will be 38.1, right? Okay. Question number 4. A triaxial test was performed on a dry, cohesionless soil, right? Under confining pressure of 144 square kilonewton per square meter. If the sample failed when the deviator stress reached to 395.8 kilonewton per square meter, determine the soil angle of internal friction. Uh, Very easy question. Can you try on this one? I will give you 5 minutes. Very easy one. This is a dry cohesionless soil. If dry cohesionless soil, very simple, you can say C is equal to 0, right? C is equal to 0. Now you want to know about soil angle of internal friction, right? You know the confining pressure, you know the deviator stress. Very easy, you can calculate. If somebody get the answer, please share on chat box. If anybody get the answer, please let me know, because I want you to try. So till now, nobody shares the answer. I don't know why it takes time. Um, so as I said, this is a triaxial test performed on a dry cohesionless soil. So very clear, C is equal to 0. And confining pressure is given. So this is the cell pressure, 144. And deviated stress also given. This is the additional pressure. So that is 395.8. So if you know the cell pressure or confining pressure, that is sigma 3. And if you know the deviated stress, then that would be the 144 plus this one would be the sigma 1. So very clear. Sigma T, sigma delta D is sigma 1 minus sigma 3. Sigma 1 means delta sigma D plus sigma 3. So as I said, 395.8 plus 144 would be the sigma 1. Since soil is cohesionless, sigma dash, sorry, C dash would be 0. So now you know sigma 3, you know sigma 1, you can draw the Mohr circle and calculate the this one, 5. Very easy. So or else you can go for this equation. It is very much easy. You know C is equal to 0. So this part will be totally 0. Right? And then you know sigma 1, you know sigma 3. Only you unknown is 5. So that you can calculate the 5. Here. This part will be 0. You know sigma 1. Sigma 1 is 539.8 we calculated. Sigma 3 given in the question. So that tan, this value will be 1.94. So that same 5 value you can calculate. Very easy. right? In each way, you can calculate this one. Even you can go for the Mohr circle, even you can go for this formula. So that you can calculate the phi value. Very easy, right? And the other thing, other question, data obtained from a drain triaxial tester as below, right? Determine the drain shear strength parameters C dash and phi dash. So how to do? Minor principal stress, that is the cell pressure, 50. Deviated stress at peak, it is given as 191 for this test. For the test number 2, minor principal stress is 100. Deviated stress at peak is 226. And then third test, we have 150 and the deviated stress is 261. So everything is given to you. What you need to calculate the C value and the phi value. Okay. So for first test, you can say sigma 1 can be calculated by sigma 3 plus delta sigma d. Sigma 3 is given as 50, and deviated stress is given as 191. So you add together so that sigma 1 can be calculated as 241 kilopascal for test 1. For test 2, you can calculate the sigma 1 on the same way. For test 3 also, you can calculate the sigma 1 in the same way, right? And draw the Mohr circle for 3 cases, have the common tangent, and then you can calculate the C value and the phi value. Very simple. And then question number 6. A consolidated drain triaxial test was conducted on normally consolidated clay. The results were a minor principal stress sigma 3 is equal to 276 kilonewton per square meter, and a deviated stress at failure is 276 kilonewton per square meter. Determine the normal stress and the shear stress on the failure plate. So normally consolidated clay, it is same like the dry sand. So that C value becomes 0, right? That is one of the observation. Consolidated drain triaxial CD test. So normally consolidated clay means C value becomes 0. And what you have to do is the minor principal stress is also given and deviated stress also given so that you can know sigma 1 value. So if you know the sigma 1 value, right? So then determine the normal stress, okay. Shear stress on failure, right? Very easy. How to calculate C dash C0, as I said. Consolidated drain triaxial test, then no pore water pressure will be there. So that sigma 3 dash and sigma will be same, right? So sigma 3 dash and sigma 3 will be 276, which is given in the question. This is this value, 276. And then sigma 3 plus sigma delta sigma d at failure will be 276 plus 276, 552. Now you know the sigma 3 value and sigma 1 value so that you can calculate the phi value because C is 0. This part is becoming 0. Sigma 1 known, sigma 3 known, only unknown is phi value. So that you substitute the values and calculate phi as 19.5. So now, what is your question? Determine the normal stress and the shear stress on the failure plate. It is not to determine phi value. It is to determine the normal stress and the shear stress at failure, right? How to evaluate that one. So let's draw our Mohr circle where C is becoming 0 and this is the sigma 1, this is the sigma 3. So we draw the Mohr circle. Tangent will be the failure envelope. So this is where the failure occurs. Now in your question, what is our source? It determine the shear stress at this point. Let me get the pen. what you have been asked to calculate the shear stress at this point and the vertical stress or the normal stress at this point. So this stress and this shear stress you need to calculate, right? So now you know these two, sigma 3 dash, sigma 1 dash. Also you know phi you calculated, right? Sigma 3 dash and sigma 1 dash, it is given in the question. Phi dash you calculated like this, right? So that you need to know this value and this value. Okay. These two values you need to know. So how to know? So I use certain trigonometry here, right? So as you know, this is the radius and this is the tangent. And here what we will have is 90 degrees, right? Here we will have a 90 degrees, right? And then from here to here, I will make a perpendicular so that there will be a 90 degree over here, right? So if we have 90 degree here, right? This value will be phi dash. This value will be 90 minus phi dash because here we have 90 degrees. This angle will be 90 minus phi dash. I hope that is clear to you. If this is 90 minus phi dash, this angle will be phi because this is also again perpendicular triangle. Okay. Hope you understood. Now this is phi dash. Since this is a right angle, this angle will be 90 minus phi dash. This small triangle, again it is a perpendicular triangle. This is 90 minus phi dash. So if so, this angle will be phi dash once again. Okay, right? So now let's talk about this sigma dash 3 and sigma dash 1. So as you know, the midpoint will be sigma 1 dash plus sigma 3 dash divided by 2. Also the radius would be, the diameter would be sigma 1 dash minus sigma 3 dash. So the radius would be sigma 1 dash minus sigma 3 dash divided by 2. Okay. So now let's get the phi dash value. Phi dash is the opposite length divided by hypotenuse length. The opposite length would be sigma 1 dash minus sigma 3 dash divided by 2. And the hypotenuse length would be sigma 1 dash plus sigma 3 dash divided by 2. Divided by 2 to divided by 2, it will be cancelling off. So that sine phi will be this value. As you know, sigma 1 dash, sigma 3 dash, you all know. So that you can calculate phi as 19.5. So that is also possible. Even from this one, you can calculate phi value, or using the trigonometry, you can calculate the phi value. Okay. Now, how to determine these 2 points, right? Let's see. ODA triangle. What is ODA triangle? ODA. This triangle, big triangle. Huh? So, 90 plus phi is equal to 2 alpha. Is that correct? This is 90 degrees. This is phi dash. 90 plus phi dash is equal to 2 alpha. Is that correct? So there's a theorem in your O levels. The the summation of internal two angles of a triangle will be equivalent to the exterior opposite angle. Okay. අභ්‍යන්තර කෝණ දෙකක එකතුව ඊට බාහිර සම්මුඛ කෝණයට සමානයි. So same way, phi dash plus 90 degrees is equal to 2 alpha. Okay. So the alpha would be 45 plus 5 divided by 2. 5 you already know, so that you can calculate the alpha value, right? You can calculate the alpha value as 54.8. Now, what is sigma dash F? Sigma dash F is this value. Sigma dash F is, you can say, sigma 1 dash plus sigma 3 dash divided by 2 minus, as you know, this length will be sigma 1 dash minus sigma 3 dash divided by 2 cos alpha, cos 2 alpha. So that's what I mentioned here. Sigma 1 dash plus sigma 3 dash divided by 2 means this length minus this length. Understood? From here to here, you know. You know the length from here to here. This length you know. If you know if you deduct this length from this bigger length, you can get this point. That's what I did. So to do that, I make sigma 1 dash plus sigma 3 dash divided by 2. That is the length from here to here. That is the length from here to here. Let me erase this one. Okay. That is the length from OA, sigma 1 plus sigma 3 divided by 2. Okay. And the balance length would be this one. Sigma 1 minus sigma 3 divided by 2 means this radius. The cos 2 alpha. Now, let me say this is actually 180 minus 2 alpha. So if you get the cos value of 180 minus 2 alpha, it will be minus cos 2 alpha. That's why it is becoming plus cos 2 alpha here. Okay. So now a little bit trigonometry, don't worry. Right here, I again repeat, from here to here, sigma 1 dash plus sigma 3 dash divided by 2. You deduct this one. So as you know, this is 2 alpha, this angle. If it is 2 alpha, this angle will be 180 minus 2 alpha. So if you get the cos of this length, this is 180 minus 2 alpha, so that it will be minus cos 2 alpha. So that's why this value become plus here. Okay. And tau phi, this value, it is very easy how to know. This is the radius length and this is phi. So that you can say, oh, you can say this is 180 minus 2 alpha, this one. So you can say this is sigma dash 1 minus sigma 3 dash divided by 2 sine 2 alpha. Sine 2 alpha. That would be this length. So the height to this, that will be the failure shear stress. Okay. So the same thing I mentioned here. So by calculating the same equation with relevant values, so you can say sigma dash F would be this 367.7 kilopascal and tau F will be 130 kilopascal. Okay. So with that, we will move to question number 7. The shear strength of a normally consolidated soil can be given by the equation tau F sigma dash tan 27, right? So you note that here C value becomes 0. That's why C plus sigma tan phi, no, normal equation. Now here C value becomes 0, because of that thing tau F becomes sigma dash tan 27. So 27 is the phi value. You have to understand like that. The results of a consolidated undrained test on the soil were chamber confining pressure 150 kilonewtons per square meter and the deviated stress at failure 120 kilonewton per square meter. Determine the consolidated drain friction angle and pore water pressure developed in the specimen at failure. Okay. So now here, normally consolidated clay, so that's why C value becomes 0. Consolidated undrained test. You notice that one. Consolidated undrained, CU test, where undrained conditions will be maintained. That means certain pore water pressure has been developed inside the soil specimen. That's why you have been asked to determine the consolidated undrained friction angle and the pore water pressure developed. Okay. Now, the same equation, sigma 1 is equal to sigma 3 plus delta sigma d. So everything is given in the question 150 and deviated stress 120. So that sigma 1 can be calculated as 270 kilopascal. So since the clay is normally consolidated, you can say C dash is equal to 0. So since C dash is equal to 0, this part will be completely 0. So sigma 1 will be only this part, right? Now you know sigma 1 and sigma 3 you know, because sigma 3 given the question, sigma 1 you calculated like this. You just substitute and calculate the phi value. Very simple, right? So 16.6 degrees. Now, what you have been asked to calculate was to determine the pore water pressure at soil. Now, you have calculated, right? You have calculated. Here you have calculated sigma 1 and sigma 3, right? All the sigma 1 and sigma 3 values are given in the question. Now, in this one, if you want to make sure, if you want to calculate the sigma dash value, the effective stress value, so that effective stress formula can be given like this, right? Now, let's say sigma 1 dash is equal to sigma 1 minus u. U is the pore water pressure. This is the total stress, right? Right here, sigma 3 dash, sigma 3 minus u. So this is again the pore water pressure, right? So you now have different equation with u values over there, right? You just substitute the sigma 1 and sigma 3 value on this equation. And then phi you calculated as 16.6, right? Accordingly, if you calculate, your answer would be 0. So developed pore water pressure will be 0. Okay. Question number 8, since we have very little time, right? In addition to this slideshow, I need to show some of the exam past paper questions related to shear strength, so that you will understand the gravity of this session, right? So question number 8, consolidated undrained triaxial test, undrained again, right? And u values are also given, right? Determine the shear strength parameters. Minor principal stress is there, deviated stress is there, u at peak. Huh? Pore water pressure is also there. So that you can calculate very easily. Now, sigma 1 plus delta sigma d would be the sigma 1, sigma 3 plus delta sigma d. So now 244 plus 200 will be the sigma 1 value. Likewise, you calculate for 3 samples sigma 1 value. And then sigma 3 dash can be calculated by sigma 3 minus u. U is given in the question. For each sample, u is given in the question. For test 1, u is 55. That's why we apply 55 here. So sigma 3 dash you know, and then sigma 1 dash you also you know, so that you can calculate sigma 1 dash and sigma 3 dash. Okay. So So these are the sigma dash value and sigma 1 dash value and sigma 3 dash value. Accordingly, for total stress and effective stress, you can draw two separate sets of Mohr circles and draw common tangents and evaluate the C value and the phi value. Question number 9. Um, an engineer is evaluating the stability of the slope in the figure below and considers that the potential for shear failure occurs along the shear surface shown. The soil has an angle phi dash is equal to 30 degrees and no cohesive strength. Compute the shear strength tau 1 at point A along this surface when the ground note table is at level B. Then compute the new shear strength tau 2 if it rises to level C. What is the absolute value difference between tau 2 minus tau 1? The unit weight of soil is 20 pounds per feet square above water table and below 123 pounds per feet cube, right? So now don't worry about these units, right? What you have been asked was the water table is maintained first at level B. So by that time we understand this is the weakest soil layer. So what we have been asked was, so first water table will be here. In that situation, what would be the shear strength at point A? And also, again the water table has been gone up, right? So up to the C point. So by that time, what is the shear strength at this point, right? So those are the two conditions you have been asked for. So, okay, let's calculate. When the ground water table less point B, pore water pressure can be calculated as U is equal to gamma W ZW. That is very clear. And then don't worry about this 20 because that 20 would be Z down. This one, 20 feet, right? What I mean, don't worry about units. Here gamma W has been applied as 62.4, but in normal situations we apply as 9.81. Since these units are different, don't worry about this 62.4. Just get the idea how to calculate. Okay. U value you can calculate in pounds per feet square. And the vertical stress at point A, you can calculate by each layer, right? 120 into 12 plus 14. Now water table is at this level. So this area will be dry. So dry layer thickness will be 12 plus 14. Dry unit weight is 120. That's why 120 into this height. 120 into 12 plus 14 plus 123. That would be the wet weight. Wet weight will be 20 feet. So that's why it is like this. And minus the U value 1248. So the finally you can get the sigma dash is at point sigma dash is at 1 as this value. So the shear stress can be calculated as sig C plus sigma dash tan phi dash. C is 0, right? So that you can calculate tan is given in this question. For phi is given in this question 30 degrees. So that the value will be 2501.1. Same calculation can be repeated for the if the groundwater table has been raised to C point. Now we calculated already for B. Same calculation we can repeat it for C water table situation. So in that situation, first you calculate the U value as previous situation, and then you calculate the sigma value. Tau value also you can calculate. So the value difference between these two will be 411.5 uh, pounds per feet square. Okay, right. So those are the examples I need to discuss with you. Believe me, I will give you some questions related to this topic. So let me show you some of the past papers I have conducted for your past batches, right? Okay, you can see now. So this is 2022 past paper. You see, first bearing capacity of a shallow foundation placed on a soft clay layer of considerable thickness. So what I am asking, what is the strength test that you need to do? And then say unconsolidated drain triaxial test was conducted on saturated sample. Likewise, it is mentioned. Shear strength parameters you have to calculate. Deviated stress at failure for second specimen. Then what is the shear strength of in terms of effective stress? Like that, it has been questioned as 20 marks. Every equation related to the question, it is given in the question paper. So you can see if you don't understand the principle, it may be difficult for you to answer this question paper. Again, this is 2023. In 2023, I say, okay, a road embankment is to be constructed rapidly on soft clay. Stability of the existing soft clay should be evaluated. What is the triaxial test? Like that, there are three examples, and then you have to evaluate. See, then more circle method you have to use and calculate this. And then direct shear test was question. So this is 2023. Then 2024 also there are certain questions related to shear. Let me show that exam paper as well. Okay. You can see consolidated drain triaxial test has been done. Okay, this is the cell pressure, for water pressure at failure, deviated stress at failure, total normal stress, like that. It is question. Then direct shear test. So like that, this has been a question in each of the exam papers. So you can see this area I may need to question. So last time also I question on this area. This time also I am expecting to have certain questions in this area. Okay. So I will share these slideshows today in your LMS. Please refer to these slideshows and you can work on these examples once again. So if you have any questions regarding these examples, please let me know in next session. Okay. So it's time to wind up the session. Thank you for joining everybody.